And welcome back. As we continue our cosmic journey, we have, of course, explored the various different types of stars, but we haven't really talked about how those stars have come to be. And so let's go ahead and take a first look at this with star formation. So let's start off by asking the question, where are stars born? Well, this image gives us a close-up of part of the Carina Nebula taken with the Hubble Space Telescope. And when we look at this image, we actually can see that there are jets that are powered by newly formed stars that are embedded here in this great cloud of gas and dust. Again, you can see them kind of ebbing out here in the various different areas. We, of course, have a nice, good visual representation here of this cloud. And you can see that parts of this cloud are actually glowing. All right, as we look at it, we can see brighter parts that are illuminated. This is because there's the younger stars recently formed within them. And so let's use that as a good jumping off point by looking at where these stars are coming from, which is molecular clouds, or as they sometimes are referred to as the stellar nurseries. The most massive reservoirs of interstellar matter are, of course, giant molecular clouds. Now, these clouds have cold interiors. They're characteristic of temperatures of only 10 to 20 Kelvin, which is pretty cold. Now, most of their gas atoms in here are typically bound into molecules, and these clouds actually turn out to be the birthplaces of most stars within our galaxy. Now, the masses of molecular clouds range from about 1,000 times the mass of our Sun to about 3 million solar masses. So we have quite a variety in size of molecular clouds. Now, molecular clouds have a very complex filamentary structure that can be up to about 1,000 light years long. So these are pretty big. If you start thinking about 1,000 light years is a pretty large distance. Think about our closest star to our own Sun is about roughly around 4 light years away. So that should help give you some context as to just how big these systems are. Now, within the clouds are cold, dense regions that are typical of masses anywhere from 50 to 500 times the mass of our Sun that we refer to as clumps. Now, within these clumps, we of course can get even closer and find denser, smaller regions that are often referred to as cores. Now, these cores are what we refer to as the embryos of stars. These are kind of where we might expect to find a star form because, again, these are very dense, small regions. Now, the conditions within these cores, where very typically are going to be things like low temperature and high density, are actually what we need to make stars. Because if the temperatures are high, that material is going to push away, and if it is low density, it's not going to have enough mass for gravity to really kick in. So the life story of any star is just an ongoing competition then between two forces. Force of gravity and force of pressure. So the force of gravity is pulling inward. It's trying to make that star collapse in on itself. Whereas internal pressure produced by the motions of the individual gas atoms pushes outward, which of course tries to force a star to expand. And if we recall, when we looked at, for example, our own Sun, we found that the reason why stars are the way they are is because they have hydrostatic equilibrium, and so the gravity and the pressure are in a pretty equal balance. Now, to form a star, we need a core of interstellar atoms and molecules to shrink in radiance and increase in density by a factor of nearly 10 to the power of 20. And that is a large, large factor. In fact, what could do this is nothing other than the force of gravity that could produce such a drastic collapse. And so let's look at this with an example here. All right, we're going to go ahead and focus in on the Orion molecular cloud to really kind of see how some of this star formation is actually happening. Now, the Orion molecular cloud is one of the best studied stellar nurseries in the constellation of Orion the Hunter, and it's about 1,500 light years away. Now, the Orion molecular cloud stretches over 100 light years, so it's not the biggest molecular cloud that we know is out there, but it is one of the most studied. Now, the total quantity of molecular gas that we find in the Orion molecular cloud is about 200,000 times the mass of our own Sun, so there is a lot of material present here. Now, most of the cloud does not glow with visible light, but actually betrays its presence by the radiation that the dusty gas gives off at both the infrared and radio wavelengths. And just to kind of give you a visual example of how this looks, we can see, for example, in image A, we can see the Orion molecular cloud. This is the constellation of Orion that we might be familiar with, and we can see it is here within the visible light spectrum. If we look at image B, you can see how much different this is, because this is the same constellation, but in the infrared with some false color added to it to really show the heated clouds that render many of the same stars that we see in visible light invisible. And this also gives us a good idea of how large the Orion cloud actually is, because you can see just how much more dense it appears when we look at infrared comparison to visible. Now, of course, we do see two nebulas in here, in both of the visible and infrared. We have the Orion Nebula and the Horsehead Nebula, which again are pretty famous nebulas. But let's go ahead and zoom in on the Orion Nebula to really try and get in on some more detail. Now, the Orion Nebula itself harbors some of the youngest stars in the solar neighborhood. If we look at image A, this is how the Orion Nebula appears in visible light. So if you had a very powerful telescope, you can go ahead and train your eye onto this nice visible light show. But if we look at this in the near-infrared radiation, we can see much more detail within the dusty nebula, since again, infrared can penetrate dust much more easily than visible light. Now, the four bright stars in the center of the visible light image are the trapezium stars. And you'll notice that most of the stars that are seen in the infrared image, again, are completely hidden by dust in the visible light. Now, studies of Orion and other star-forming regions actually show us that star formation is not a very efficient process. You might think that, physics has this down, but, it's not as efficient as it should be, because even when we look in the region of the Orion Nebula, only about 1% of the material in the cloud has actually been turned into stars. This is why we can still see a substantial amount of gas and dust near the trapezium stars. The leftover material that we see is eventually heated, either by radiation and winds from the hot stars that form, or by explosions from the most massive of stars. Now, whether this material is moved gently or explosively, we find that the material in the neighborhood of new stars is simply blown away into interstellar space. Now, older groups or clusters of stars can then be easily observed in visible light because they're no longer shrouded in things such as dust and gas. And although we do not know what initially caused the stars to begin forming in Orion, there is some good evidence that the first generation of stars triggered the formation of additional stars, which then, of course, turned to lead the formation of still more stars. And we call this propagating star formation. So star formation can move progressively through a molecular cloud. The oldest group of stars has expanded because of the motions of individual stars, and we can see that here represented in this image. Now, eventually the stars in that group are going to disperse and no longer be really kind of recognizable as a cluster. They will just kind of move away from one another. Now, the youngest group of stars lies next to the molecular cloud, as we can see again in this image, and they're typically only about 1 to 2 million years old, and the pressure of hot ionized compressed material in the edge of the molecular cloud actually initiates some of that gravitational collapse that will eventually lead to the formation of more stars. And this process will continue to repeat itself. The older stars will, of course, expand out. They will eventually no longer be a cluster. The younger stars will remain near to that molecular cloud, and they'll form, push it, and again, the process kind of repeats. The basic idea of triggered star formation is this. When a massive star is formed, it emits a large amount of ultraviolet radiation and ejects high-speed gas in the form of stellar wind. Now, this injection of energy heats the gas around the stars and actually causes it to expand, because again, it has energy. Now, the massive stars eventually exhaust their supply of fuel, they explode, and then that energy of the explosion also will heat the gas. So again, another source of energy to cause expansion. Now, these gases eventually are going to pile into the surrounding cold molecular cloud, compressing the material into it and increasing the density. Now, if this increase in density is large enough, gravity will overcome pressure and stars will begin to form in the compressed gas, effectively starting the whole cycle all over again. Now, there are many molecular clouds that form mostly low-mass stars. Because low-mass stars do not have strong winds and do not die by explosion, triggered star formation cannot occur in these clouds. There are also stars that form in relative isolation in small cores. Therefore, it's important to note that not all star formation is actually triggered by the death of massive stars. So let's now, with all that in mind, look at the birth of a star. How does this actually happen? Well, the first step, of course, is the process of creating stars is simply that formation of those dense cores within a clump of gas and dust. So going back to those molecular clouds we were just talking about, we see these core regions, and eventually gravitational forces of infalling gas become strong enough to actually overwhelm the pressure exerted by cold material that forms these dense cores. Now the material then undergoes a rapid collapse, and the density of the core increases greatly as a result. Now, during the time a dense core is contract and become a true star, but before the fusion of protons to produce helium begins, we call this object a protostar. So the protostar stage is really kind of effectively a baby star. And so here we have a nice good visual representation of how that birth of a star actually occurs. First, of course, we have dense cores forming within a molecular cloud. A protostar, then, with a surrounding disk of material, forms at the center of the dense cloud, really kind of starting to accumulate additional material from within the molecular cloud through things such as gravitational attraction. Then, of course, we have stellar wind, is going to break out but be confined by the disk to flow out along the two poles of the star. So it's got stellar wind, it's pushing things out. And eventually this wind, of course, is going to sweep away whatever cloud material that was around the star and halts the accumulation of additional material, and a newly formed star surrounded by a disk then becomes observable. Now, once almost all the available material has been accreted and the central protostar has reached nearly its final mass, we give this a special name, a Titari star. Now, only stars with masses less than or equal to that of our own sun become Titari stars. Massive stars do not undergo this stage. In fact, they tend to skip it completely. And so that's going to get us into kind of one of our final pieces here, which is talking about the winds and jets that these stars encounter. Because Titari stars may be stars actually in a middle stage between that of being a protostar and a hydrogen fusion star, such as our own sun. In fact, we have high-resolution infrared images that reveal that there's actually jets of material as well as stellar winds coming from some Titari stars. Now, a stellar wind consists mainly of protons and electrons that are streaming away from the star at speeds of a few hundred kilometers per second. Now, this is, again, pretty fast, because when the wind actually first starts up, the disk of material around a star's equator blocks the wind in its direction. So where the wind particles can escape most effectively is, again, in the direction of the star's poles. Now, on occasion, the jets of high-speed particles streaming away from the protostar collide with a somewhat denser lump of gas nearby. They excite its atoms and cause them to emit light. Now, these glowing regions, known as Herbig-Haro or HH objects, allow us to trace the progress of a jet to a light year or more from the star that produced it. So it's actually a very good way of tracking some of this. Now, the wind from a forming star will ultimately sweep away the material that remains in the obscuring envelope of dust and gas, leaving us with, again, the naked disk and protostar, which can then be seen with visible light, as we saw in our image.